Okay, guys, so here we have four different units that were derived through manipulating the math. All right, so these, when we set up our dimensional analysis, these were the units that were left over. So what we have done is we've created new two-dimensional units that can be used to convert or be used to explain a scientific phenomena. So when we look at units like this, what does it tell us? Like, what do they mean? All right, what happened? All right, so here what I can tell you, when I look at this first value, it tells me actually a lot. So I can look here and I can say, okay, well, this value of 52, it was created by taking the kilograms and dividing it by centimeters cubed. All right, we can also look at it as 52 kilograms over centimeter times centimeter times centimeter, right? So some type of mass, and we already know that a centimeter times centimeter times centimeter or centimeter cubed is a volume. So some type of mass divided by its volume. That's how that number was obtained. Well, we can also look at it in the eyes of a conversion factor. If you remember when we were looking at metric conversions, this is an equality statement. This equality statement says that 52 kilograms of mass is equal to 1 centimeter cubed. So now that we can look at this two-dimensional unit that we derived through unit conversions, we can now make it into a statement. So we made it into an equality statement. So 52 kilograms in this instance is equal to 1 centimeter cube. So now we can help use this to make predictions, to see, okay, well, if we had 7 centimeters cubed, what would that mass look like? All right, see, it tells us something. All right, let's look at this next one. So here we have another two-dimensional unit. And when I use the word two-dimensional unit, that means we've got a unit in the numerator and we have a unit in the denominator. And like I said, these are really important because we can use these as equality statements to make predictions for something that we didn't actually measure when we plug them into the equalities. So here we have the value of mole, which is a unit that represents an amount of a substance, over liter, which is a volume. So amount of substance per volume. That's what that's saying to me right there. So we have 9 moles per liter. So what does that mean? Well, that means that for every 9 moles, we have 1 liter. So again, with this equality representation, we can make predictions. If we had 13 moles, how many liters would that be based off the statement? It's really, really important because it allows us as scientists to predict a scientific phenomena based off of a model. And this is a numerical model. All right, let's look at this two-dimensional unit. So we have 3.9 moles over kilograms. So we have an amount of substance per mass of substance. So what this does is it works the equality. 3.9 moles amount of substance equals 1 kilogram. Again, this equality tells us something. So now based off of this mathematical model, we can now make predictions. Well, if I had this substance and I had 5 kilograms of this substance, how many moles would that be? Or we could say, well, if I only had 0.5 moles, how many kilograms would that be? Again, allows for prediction. And then last here, we have millimeters of mercury. Millimeters of mercury is a unit we're going to see in the gas laws unit, and it came about from using a barometer which had mercury in it, and as the atmosphere pressed down on the barometer, it made the mercury levels go up or it would not move. So we would measure the distance that it moved from its starting point and we get the unit millimeter of mercury. Long explanation, all it does is it's a pressure. Okay, it's an air pressure. So here we have millimeters of mercury per Kelvin. Kelvin is a temperature we use is a temperature unit we use in chemistry. We don't use Celsius very often, and we don't use Fahrenheit very often because Kelvin is based off absolute zero. And we're going to get into that again during the gas laws, but it's a temperature unit. So we're looking at the air pressure per the temperature. And so again, this two-dimensional unit. It tells us something that allows us to make predictions for values that are not physically written down. All right. So here for this particular situation, we have 0.5 millimeters of mercury for every 1 degree Kelvin. So this tells us a lot here because this tells us that if we have a specific temperature, we can figure out what the air pressure would be. Again, another prediction. So deriving units and creating these two-dimensional number models allows us to make predictions based off of the equalities they represent. So for the situation here with the 0.5 millimeters of mercury per 1 Kelvin, we could say, okay, well, if I had an air pressure of 7 millimeters of mercury, what could I predict the temperature to be? Or if I knew the temperature was -5 degrees, let's not do that one. Let's say we had 275 degrees Kelvin. What would the air temperature be then? So these conversion factors, these equality statements, or these two-dimensional units, they allow for us to make predictions based off of the situations that they came from.